Now, one interesting thing to talk about is the phasor diagrams for resistors, capacitors, and inductors. For resistors, last video we saw the relationship V equals IZ. So we were just talking about a resistor. Given that ZR is equal to R, the relationship for the phasor diagram just simply looks linear, almost the same as what we've seen with a resistor when we're plotting its current voltage relationship. For capacitors, on the other hand, we have J divided by omega C. Now, what ends up happening is that just for this case, so this is for resistors, for capacitors, we have, whoops, for capacitors, we have the following. With respect to the resistor, the capacitor is always 90 degrees out of phase compared to the resistor. For the inductor, we have J omega L. With respect to the resistor, the angle is always 90 degrees out of phase. So, what is this observation? Resistors are in the case that current and voltage are in phase. Same phi, for example. For capacitors, current leads voltage by 90 degrees. And we're talking about the case of purely resistive, purely capacitive, and purely inductive. While for inductors, current lags voltage by 90 degrees. Now, just to give you the kind of intuition, it makes sense because for an inductor, you model the voltage as the derivative of current, while for capacitors, you model the voltage, while you model the current as a change in voltage. As such, usually capacitors make the current lead the voltage, while inductors lag the voltage. Now, why would we want to care about these phasor diagrams? Because they tell us something we want to care about later on called power factor. Later on, we'll talk about power and the different types of power associated with, well, talking about power factor. And in one of these, you don't want, or you ideally want in phase systems because this is how you basically limit the amount of current that is absorbed by capacitive or inductive elements. So if you had like a leading system compared to the voltage, it would be ideal to maybe add an inductor to lower the phase so that maybe it points like so instead. Similarly, if you had an inductive system, you'd maybe want to pull it up by adding a capacitor. So maybe add, oh, sorry. So add capacitor, add inductor. For this one, add capacitor. If we look at the general formula in the case of series impedance, Z is equal to R plus J X, or R plus J omega L minus 1 over omega C. If these two are equal to each other, we get the ideal situation, which is when impedance is just purely resistive, and that allows us to get the maximum amount of power. But there are other problems associated with this, which you'll see in EE 3030. But for now, phasor diagram wise, it looks something like this. So let's say that the resistor kind of looks, let's choose a brighter color, look like this. So this one's just modeling a resistor. No problem. A capacitor is always 90 degrees, or a capacitor makes the current, a purely capacitive system makes the current always 90 degrees out of phase with the voltage. So this is in the case of a capacitor. And just as a note, we're talking about purely. Resistive, capacitive, and inductive systems. Okay. And then lastly, for the case of inductive, it's always 90 degrees lagging the voltage. So inductive. So this is always 90 degrees. This one's also 90 degrees. So for resistors, in phase. For capacitors, I leads V by 90 degrees. For an inductor, I lags V by 90 degrees. Now, what if you have multiple elements, resistors plus capacitors, resistors plus inductors? Then it's not necessarily 90 degrees based on this equation. You still have to kind of find the angle of it. And that's no problem, really. By having this R plus JX, you can find the angle of impedance, which is equal to tangent inverse of X divided by R. No problem. And you'll maybe find some angle in between once you introduce resistors and capacitors. For the case of RCL systems, it really kind of depends on what value you're given. But go back to complex algebra and kind of see the different cases that are presented, and we apply the same amount of cases here. Okay, thank you.